is a device that produces a beam of fast-moving, electrically charged atomic or subatomic particles. The effectiveness of an accelerator usually is characterized by the kinetic energy rather than the speed of the particles. The unit of energy commonly used is the electron volt, which is the energy acquired by a particle that has the same magnitude of a charge as has the electron when it passes between electrodes that differ in potential by 1 volt. Related larger units are the kilo electron volt, which is 1000 electron volts, the mega electron volt, which is 1 million electron volts, the giga electron, which is 1 billion electron volts. Compared with the quantities of energy encountered in everyday experience, even 1 billion electron volt is a very small amount, about that gained by a grain of salt as it drops 1 millimeter under the influence of gravity. The masses of the particles accelerated are so small, however, that kinetic energies in this range correspond to very high speeds. The speed of the particles in the smallest ion accelerators is about 5,000 miles per second or 8,000 kilometers per second, which is about 3% the speed of light. The particles that are accelerated are electrons, positrons, positive electrons, or ionized atoms such as protons, ionized hydrogen, deuterons, ionized heavy hydrogen, alpha particles, ionized helium, or heavier ionized atoms. Sometimes the primary beam is used. In other cases, the primary beam is directed onto a target to produce a beam of secondary particles, such as gamma rays, neutrons, mesons, hyperons, or neutrinos. A few accelerators are operated as sources of the intense radiation called synchrotron radiation, emitted by electrons moving at almost the speed of light along curved paths. Physicists use accelerators in fundamental research on the structure of nuclei, the nature of nuclear forces, and the properties of nuclei not found in nature, such as the transuranic, heavier than uranium elements, and other unstable elements. Accelerators are also used for radioisotope production, industrial radiography, cancer therapy, sterilization of biological materials, and polymerization of plastics. The largest accelerators are used in research on the fundamental interactions of the elementary subatomic particles. Every accelerator has 3 essential parts: a source of the particles to be accelerated, a vacuum chamber in which to accelerate them, and a source of the electric fields needed to effect the acceleration. Thermionic emission, the emission of electrons from the surface of a heated solid, is the process used to provide electrons. Positrons are produced as secondary particles by an electron accelerator and then further accelerated. Positive and negative ions are produced by electric arc or glow discharges in a gas at low pressure in the chamber. A high voltage electrode extracts the ions from the gas through a hole in the chamber. The region in which the particles are accelerated must be highly evacuated to keep the particles from being scattered out of the beam or even stopped by collisions with molecules of air. Accelerators are differentiated by the derangements of the accelerating electric fields. In a linear accelerator, the path of particles is a straight line, and the final energy of the particles is given by the sum of voltages produced by the accelerating devices along that line. In a cyclic accelerator, the path of particles is bent by the action of a magnetic field into a spiral or a closed curve that is approximately circular. In this case, the particles pass many times through the accelerating devices. The final energy depends on the magnitude of the voltages and on the number of times the particles pass through. Because the total distance traveled by the particles in a cyclic accelerator may be as much as a million precisely.